The next talk is about reducing the share size of weighted threshold secret sharing schemes with a Child's parameter approximation by Oriol Faras and Michael Guillot. And Michael is giving the talk.
Thanks for the introduction. And well, this is a joint work with my advisor, Oriol Faras. And our work is mainly about secret sharing schemes, which is this cryptographic primitive that allows a dealer to share a secret among a set of parties in such a way that only authorized subsets of them can recover it. So for example, if our dealer wants to secret share the secret with this group of 4 people in such a way that only by joining the shares of the 4 participants they get the secret, they will use a scheme like that, no? So that when the 4 group of people join their shares, they get the secret, but also we require that whenever a subset is not authorized, they gain no information at all about the secret. In this setting, there's a notion of the access structure, which is the family of authorized subsets of a secret sharing scheme. And for example, in the previous case, was simply corresponding to the subset of the 4 participants. These access structures can be expressed as monotone Boolean functions where the input bit string corresponds to a subset of participants that gets mapped to 1 whenever they are authorized or to 0 whenever they are forbidden. Among all the access extractors in our work, we focus on weighted threshold access extractors in which each participant has an associated weight, and then the authorized subsets are those whose total weight is at least a threshold value. In order to talk about these weighted threshold access extractors, we need to introduce the Shamir secret sharing scheme that probably most of you know that works for the threshold case. In that case, the dealer simply constructs a polynomial where the 0 coefficient corresponds to the secret and the other coefficients are simply random values from a finite field, and then sends one evaluation point to each of the parties in such a way that whenever a subset reaches a threshold, they can recover it simply by doing polynomial interpolation and then evaluating to 0 to get the secret. So we can use this secret sharing scheme using virtualization, which means sending, instead of one single share to each of the parties, send as many shares as its associated weight, precisely to realize weighted threshold access extractors. And this gives a share size which is almost linear in the weights of the parties. So this scheme is pretty efficient for these access extractors in the case that there exists a representation of this weighted threshold function whose weights are small. However, there exist weighted threshold access extractors that require weights of exponential size. And for these particular cases, this scheme is not efficient enough. As an alternative, we could use the construction of Weimel and Wenrep that basically gets quasi-polynomial share size for these access extractors, and is the one that is the most efficient node to date for these access extractors. Unfortunately, this is still not enough, as nowadays there are multi-party computation protocols and consensus mechanisms, as for example proof-of-stake blockchain networks, that precisely require efficient schemes for this weighted threshold access extractor. So for this reason, nowadays the state-of-the-art idea is to try to relax the restrictions on this kind of access extractors to get more efficient schemes. And this leads to the definition to what is known as the RAM setting, the RAM weighted threshold access extractor, where now instead of having one simple threshold, we have 2 different thresholds. And the subsets whose total weight are below the lowest threshold, we say that they are forbidden and get no information of the secret. And the ones that are above the greatest threshold are authorized. What happens with the subsets that are in between? Well, who knows? They could be either forbidden, authorized, or get partial information, so they are not precisely defined. In this setting of the RAM-weighted threshold access extractor, in the last couple of years, there have appeared plenty of works that precisely get more efficient schemes, so they reduce the share size of secret sharing schemes precisely by realizing this weighted threshold, these RAM-weighted threshold access extractors instead of the weighted usual ones. So in that context, there's a question, no, that maybe it's a natural question to ask. This, okay. How close are these RAM-weighted threshold access extractor to the weighted threshold ones? So for example, if we have a weighted threshold access extractor and we move towards the RAM setting, a question to answer here is how many subsets of the previous weighted threshold access extractor fall into this gap that is generated by both thresholds. Instead of answering this question, in our work, we slightly change the approach. And what we do is, given a weighted threshold access extractor, we approximate it by another weighted threshold access extractor. So we don't go to the RAM setting, but instead, we construct another weighted threshold access extractor. And the question we answer is how many subsets change their condition of being authorized or forbidden from one access extractor to the other. So in that context, our main goal is to find a good trade-off between the efficiency and the accuracy of the approximation. So on one hand, we want to build efficient schemes, so schemes with almost linear share size. But at the same time, we want to keep track of the fraction of subsets that get modified along this process. So our main result is the following one that basically says that given any weighted threshold access structure, you can build another weighted threshold access structure that is pretty close to the original one. So the fraction of subsets that change their condition tends to zero as the number of parties increases, in which you can build a secret sharing scheme whose share size is almost linear in the number of parties. In order to prove the result, we use tools from complexity theory, and in particular from the analysis and approximation of Boolean functions. And the general idea of our approach is the following one. So given our weighted threshold access structure, we want to build another one which is pretty close to the original one. What we do is first, we view it simply as the monotone weighted threshold function, and now in this richer framework of complexity theory, we will try to approximate it. First, we'll compute a notion known as the Chow parameters of this weighted threshold function, and we'll slightly modify them to obtain the Chow parameters of another weighted threshold function. And once we have them, we simply will compute again its associated weighted threshold function. And finally, we will view this function simply again as an access structure. By performing this longer path, we can keep track at each of the steps of how many subsets are getting modified from the original access structure to the new one. So let's dive a little bit into the details. And first, to introduce the notion of the Chow parameters, since indeed they are the low-degree coefficients of the Fourier expansion, it's useful to work with the domain 0, -1, 1 domain in the Boolean functions instead of the 0, 1, for technical reasons that I will not enter. In that context, we can also define them simply as being these expected values that you can see in the slide. And indeed, they are interesting precisely because any weighted threshold function is uniquely determined by its Chow parameters within the space of Boolean functions. So instead of working with this kind of function, we can simply look at its Chow parameters. Moreover, since we want to approximate them, we also need to take into account the notion of the distance between Boolean functions, that in this case simply correspond to the fraction of inputs in which they differ. And the distance between the Chow distance between both functions simply corresponds to the Euclidean norm between the Chow vectors of the function. Moreover, it's also interesting to point out that we can relate both notions of distance, as a small distance between Boolean functions implies a small distance in the Chow parameters, and the other way around. So if we pack this everything together, what we can get is precisely the intuitive idea that maybe we can use the Chow parameters precisely as the building block for approximating weighted threshold functions. So let's do this, and in that context, our main technical result is the following one that basically says that there exists a randomized algorithm that given a monotone weighted threshold function, it outputs another monotone weighted threshold function, but that has these additional properties. First, the output function is epsilon close to the original one. So it's a function that is pretty close in its behavior to the one that you had as an input. And moreover, and this is the key point for building later efficient schemes, is that the weights of this output function are upper bounded by the bound that you can see in the slide. That is sublinear in the number of parties and has a quasi-polynomial factor in the inverse of the error. If we compare this upper bound with the one that was given for that there exists weighted threshold function with exponential weights, what we get here is that the function that this algorithm is outputting has particularly small weights. So this is what will enable us later precisely to build more efficient schemes. Some remarks about the result. The first one is that this is an adaptation of the work of De, Diakonicolas, Feldman, and Cervedio to the monotone setting. Since we are working with access structures, we need them to be monotone. And moreover, this approximation algorithm also preserves the influence of the coordinates and the weight hierarchy. That basically means that if before approximating a coordinate was, for example, the one with the largest weight, after approximating, you can guarantee that this coordinate still has the largest weight. And moreover, that the fraction of inputs in which it affects the output of the function is still preserved. So having this result, let's now build precisely the efficient schemes. So how we do that? Well, the idea of this algorithm goes as following. First, we have our weighted threshold function, and what we do is we compute its Chow parameters. When we have its Chow parameters, we build a candidate function that corresponds to the function that has per weights precisely the Chow parameters of the original function. In order to check if it's close enough, we compute its Chow parameters and simply check if the Euclidean distance between both functions, or the distance between both Chow distance, is small enough. If it's not the case, what we do is we compute a function h of x that in some sense kind of corrects our candidate g for being closer to x, and then we define our new candidate function g of x to be precisely our previous candidate plus this correction function. So we compute again its Chow parameters and check again if the distance is enough. It can be seen that this process finalizes in a polynomial number of steps, and when this happens, you simply output our function g of x. So this is more or less the idea behind this approximation technique. And now that we have, let's say, this approximation done, let's build the efficient scheme. So we come back to our main result and see a little bit how we prove it. First, the first step we do is basically we discard from our weighted threshold access structures all parties whose weight are pretty small. And once we have these parties discarded, what we do is, with the remaining parties, we approximate them using precisely this algorithm. By performing these two steps, what we guarantee is that the weights of the output function g of x are of size almost linear in the number of parties. So since they are really small, what we can do at the end precisely is to apply the Shamir secret sharing scheme with virtualization to this new function. And this is the way we get our efficient scheme. As a side note, in our work, we also look at some computational version of schemes for these weighted threshold access structures, and we see that more efficient schemes can be built. With this in mind, just some closing remarks and open questions regarding our work. And the first one is that we've seen that the share size of existing weighted threshold secret sharing schemes for weighted threshold access structures indeed have a strong dependency on the size of the weights. And in order to circumvent this limitation, the state-of-the-art solution is precisely to try to find a good trade-off between the efficiency of the schemes and the accuracy of the approximation. And in this context, our proposal ensures almost linear share size at the cost of a tiny error. As I said, also moving towards the computational setting allows nowadays to build more efficient schemes. And some open questions relating our work. The first one is that it would be nice if we were able to build secret sharing schemes with polynomial share size for weighted threshold access structures, but without the need of approximating them. Moreover, another interesting question to work on is to try to improve the known lower bound for these access structures, which right now is simply the square root of n. So there's still a big gap between this lower bound and the known upper bound, which is quasi-polynomial in the number of parties. So this is something, there's margin of improving there. And finally, this is more application-oriented, but it would be nice to try to find a relation between our notion of approximation and the RAM criteria, and be able to move from one to the other and see if there are some relation there. That's all. Thank you for your attention, and if you have any questions, just let me know.
Any questions? If not, I have a question. So when we look at the approximation functions, sometimes for some, let's say, subset of parties that has weight very closer to the threshold, maybe we are more willing to make an approximation for this subset versus another subset that is cumulative weight is much lower than the threshold. So does your approximation, this epsilon factor, takes this into account, or?
Well, yeah, that's a good question. Indeed, our approximation takes into account, let's say, the whole set of subsets possible. So it's not specifically targeted to some of them, but as I said before, what it preserves is in some sense, the influence or the capabilities of each specific parties, but not as a group of them.
Yeah. So I understand. So I'm just saying that, for example, for the RAM setting, it's more acceptable because we are not going to make an approximation for parties whose weight is very, very lower than the threshold. So in that sense,
sorry. Okay. In this regard, this is related with the last open problem that we told. We were looking at trying to find some way to move from one setting to the other, to the RAM setting, just to cover these kind of concerns. But this is still work in progress and we have no good result for the moment. But intuitively what we get is that since the function is monotone, if there's the worst case that would be, for example, a subset that is forbidden with small weight gets accepted after approximating. Yeah. This would imply that all the subsets that are above this but also are forbidden, they would be also authorized, so the error would increase a lot. Okay. So intuitively, this is, let's say, a reasoning why this should not happen, but this is still work in progress.
Okay, cool. Yeah. If no more questions, let's thank the speaker again.